All right, so we've talked about fluids whenever they're stationary, but now we need to think about fluids whenever they're in motion. So, one difference between moving fluids and static fluids is that a moving fluid can exert a force parallel to any surface over or past which it flows. So, a static fluid cannot do this. So, since the moving fluid exerts a force against the surface must also exert a force on the fluid, right? Newton's third law. So, this is the viscous force, which we'll talk about in a little bit, and the viscous force opposes the flow of the fluid. It's kind of like the counterpart to the kinetic frictional force between solids. So, fluids in motion and fluid flow itself can be characterized as either a steady flow or an unsteady flow. So, when the flow is steady, the velocity of the fluid at any point is going to be constant in time. So, a steady flow is laminar, like we see here in the incense smoke, right? So the part of this fluid that looks very consistent, very steady, is the laminar flow of this fluid. Remember, fluids can be liquids or gases. In this case, we have like a gas, right? It's smoke. So the fluid flows in neat layers so that each small portion of the fluid that passes by a particular point follows the same path as every other. That's how we get this smooth laminar flow. So the path that the fluid follows, starting from any point, is called a streamline. But whenever the fluid velocity at a given point changes, then the flow of this fluid becomes unsteady, right? And we encounter things like turbulence. So turbulence would be like an extreme example of unsteady flow. And in a turbulent flow, we get swirling vortices that start to appear. So these vortices are not stationary, they actually move with the fluid, which is what we see in this portion of the smoke over here. You see this vortexing starting to occur, or this eddy current that's occurring. So the flow of the velocity at any point changes erratically. Prediction of the direction or speed of the fluid flow is incredibly difficult. So what we're going to be focusing on in this class is mostly going to be steady fluid flow. So whenever we're talking about the motion of fluids, we have to define what type of fluids that we're talking about. And so for this class, we focus almost strictly on ideal fluids. And ideal fluids have a couple of properties. The first is that this fluid is non-viscous, meaning that there's no internal frictional force between adjacent layers of this fluid. The other is that we assume that this fluid is incompressible, meaning just that its density is going to be consistent at any location. Also, like I said, we assume that the fluid motion is steady, so the velocity, density, pressure at each point in the fluid is not going to change with time, right? We have this streamline flow instead of turbulent flow. And we assume the fluid moves without turbulence, right? So this implies that each element of the fluid has zero angular velocity about its center. So there can't be any currents that are present in the moving fluid. And if we were to like place a small wheel in the fluid, it would translate, but it would not rotate, meaning that this wheel would like float forward without any rotation to it. So the first equation we're going to think about is something called the continuity equations. So the continuity equation is just a principle of conservation. It's a conservation law, specifically for the conservation of mass for fluids. So it basically tells us that whatever goes into the pipe has to also come out of the pipe. So we're assuming that there is no fluid that is being added or removed at any point in between. So whatever fluid I put in one end of this tube has to come out the other end. So we can make the statement that the mass of the fluid that goes in is the same as the mass of the fluid that comes out. We can say again that density is equal to mass divided by volume. So because it's easier for us to think about the density of a fluid, which is something we can generally look up, or it can be easy to determine through like the specific gravity, and we can generally calculate the volume of a fluid. easier than we can determine what is the mass of a fluid, right? So we want to represent this with density and the volume because these are the easiest things for us to determine for something like a fluid. So I'm going to replace the volume with information about the cross-sectional area as well as the x value, the distance that is being traversed over some period of time, right? So I'm just replacing volume with area times like height or length, right? Because this is the same as volume. We can state that our change in position is equal to the velocity of the fluid times the change in time, right? This is straight out of kinematics, average velocity, change in position divided by a change in time is equal to velocity. I just rearranged that. And now we can learn about the density, the area, the velocity, which we could calculate if we put like an apparatus on the end of like a hose. We can figure out how quickly this fluid is moving by some change in time. So we can assume that the density that goes in is the same density that comes out, meaning if I put water in, oil isn't going to come out the other end, right? It's not a magic tube. If water goes in, water comes out. We're also going to assume that we are thinking about the same period of time. So if I think about 3 seconds going in one end, I also want 3 seconds coming out the other end. So that means that our density and our time go away, and our continuity equation is just that area 1 times velocity 1 has to be equal to area 2 times velocity 2. So we can see this where if I have a garden hose, right, the area of the garden hose, the cross-sectional area, remains the same, meaning that the velocity that water comes in is the same velocity that the water comes out. I can change this, whereas if I put my thumb on the end of this garden hose, I am increasing the velocity. That's because as my area went down, my velocity had to increase to maintain this continuity equation. So streamlines are closer together where the fluid flows faster and further apart where it flows more slowly. So if I have a tube, right, and it has a smaller cross-sectional area, it's going to be moving quicker through the smaller area than whenever this thing opens up and I have a larger area, because increase area, decrease velocity. So my velocity decreases, my streamlines are further apart. So streamlines can help us visualize fluid flow. And the fluid velocity at any point is going to be tangent to the streamline through that point. So we can calculate things like different types of flow rates. So we have mass flow rate, which is our change in mass over our change in time. This is going to be density times area times velocity. We also have volume flow rate, and this volume flow rate is what we see in the continuity equation. So our continuity equation is actually the volume flow rate at point 1 has to be equal to the volume flow rate at point 2. We can also calculate the work done by a fluid. So the work done by a fluid is going to just be the difference between the work that happens at point 1 and the work that happens at point 2. So our definition for work is going to remain the same, force times some change in position. But we need to change this force into something that we can use for fluids. Well, we can use pressure and area for a fluid. So this changes our work into pressure times area times a change in position, or pressure times volume. Now this PV you've probably seen before. You've probably seen that before in like an ideal gas law, which we'll get into a little bit later. But work done by a fluid, the work at point 1 is the pressure at point 1 times the volume at point 1. At point 2 it would be pressure 2, volume 2. So you'll notice in my picture here that my cross-sectional areas are different, but I'm actually going to choose my delta x so that my volumes are exactly the same. Meaning, for side 1 that has a larger area, I pick a smaller delta x, and for my side that has a smaller area, I pick a larger delta x. And I do this so that my volumes are going to remain the same, and I can represent the work done by a fluid as my change in pressure times a volume. This leads us to the work energy theorem for fluids. So I can state that the initial kinetic energy plus the initial potential energy plus the work done by the fluid is equal to the kinetic energy final plus the potential energy final, right? So we've seen this before whenever we were talking about the conservation of energy with mechanics and like a ball dropping or rolling down a cliff. We're going to do the same thing but with fluid. So the work done by a fluid is this change in pressure times the volume. So I use my standard kinetic energy, and I'm going to use potential energy due to gravity. Why? There's not a spring in my fluid. In this picture, I do have a change in height of this tube, so I will have a change in my gravitational potential energy here. So I'm going to expand this out, and I can move all of my initials to one side, all of my finals to the other side, but I need to replace all of these masses with density times volume. Why? Because it's easier to figure out the density of a fluid and the volume of a fluid than it is to figure out the mass of the fluid. I do want to point something out right now. Notice that my velocities have a vector sign on top of them. My volumes do not have a vector sign on top of them. We have two different types of V's in this equation. We have volumes and we also have velocities. I replace all of my masses with density times volume, and I notice that in every single term of this equation, I have volume. So all of these volumes cancel out, and it gives me this equation that represents essentially the conservation of energy for fluids. So this is called Bernoulli's equation. It's pretty much the conservation of energy, but for fluids. So we have information about the pressure, we have information about the kinetic energy, and we have information about the potential energy for the initial and the final conditions. You will approach these problems almost exactly the same way as you did our conservation of energy problems. One thing that's important to note is that Bernoulli's equations only work for ideal fluids, right? That are non-turbulent, that are non-viscous, that have streamlined flow. So what happens whenever we have fluids that have viscosity or this fluid friction, right? All real fluids have some sort of viscosity to them. So to maintain flow in a viscous fluid, we have to apply some external force, since viscous fluids this viscous force opposes the fluid flow, kind of like friction opposes the motion of an object. Viscosity opposes the forward motion of a fluid. So a pressure difference between the ends of a pipe must be maintained to keep a real liquid moving through some sort of horizontal pipe. So this pressure difference is what is providing that force to overcome a viscosity. So viscous fluids have some sort of resistance to flow. Whenever we stop and we think about like what is a low viscous fluid, what is a high viscous fluid, it does come fairly intuitively. Like if I ask you what is more viscous, water or honey, naturally we would say honey. Why? Because it flows slower, it has high viscosity. So things like syrup, molasses, motor oil, honey have high viscosity. Other things that flow very easily, like water, alcohol, air, gasoline, these are very low viscous fluids. So viscous fluid flow looks a little bit different than non-viscous fluid flow. So whenever we have a non-viscous flow, all of our velocities are equal. Each layer of the fluid has the exact same velocity, and they slide past each other with no resistance. Whenever we have a viscous fluid flow, though, our velocities are different, meaning that the velocity at the edges of the pipe are much, much smaller than the velocity in the center. And this is because we have forces between the wall of the pipe and the fluid that slow this down, right? This is because of the forces between molecules of the fluid and the actual molecules of the wall. So the viscosity, or the internal friction of a fluid, is represented with this Greek letter eta. It kind of looks like a really fancy cursive N. We can also see that you can have fluids that have different viscosities at different temperatures. So water, whenever it's cool, has a higher viscosity than water whenever it has been heated up. And that's because whenever you heat it up, you start to break the bonds between the molecules, so things flow a lot smoother. And whenever we're thinking about the rate of flow of a viscous fluid, we're going to think about, I call it Pascal's law, but I know that's not right. It's Puiseux. That also sounds terrible. I don't speak French. I can't pronounce French. This smart fella's law tells us how much fluid flows depending on things like the pressure difference in the tube, the radius of the tube, the viscosity of the fluid, and the length of the tube. So this is our flow rate for viscous fluids. This shows us that the difference in pressure is actually what's causing this fluid to flow through the tube. So the rate of flow, or the volume per unit of time, depends on this pressure difference as well as the dimensions of the tube and the viscosity of the tube. So we can actually break this equation down a little bit. So we can look at two different parts of this equation. We have the volume flow rate, right? So this force is the pressure difference, and my R here is not the radius, but it is my resistance to flow. So things that are resisting the flow. It would be stuff like the viscosity, how long this tube is, right? So the longer the tube is, the more, the greater of a pressure difference you would need to maintain a flow rate. The same thing with the larger the tube is, the more pressure you would need to maintain this flow rate. So to maintain a constant flow rate, the pressure difference must increase as the viscosity of the fluid increases. So if we think about this applied to blood through our circulatory system, right, as the viscosity of blood increases, as the number of red blood cells rise, blood with a high concentration of red blood cells requires greater pumping pressure from the heart to keep it circulating than blood that has a lower concentration of red blood cells. Also, the radius of the tube is raised to the fourth power. So this means that a small change in radius makes a drastic difference. So if a constriction occurs in a vein or an artery, the heart will have to work considerably harder to produce that high pressure drop that's needed to maintain a required flow rate. That's why even just a little change in your the radius of your artery results in a huge strain on the heart. So the radius matters most in this equation, right? Flow is proportional to the fourth power. Tiny changes cause huge changes in flow rate. So if I just double the radius, I need 16 times more flow. I need 16 times more pressure. Pressure increases the flow, right? So more pressure difference, more flow. And viscosity and length, right? Thicker fluid, slower flow, longer vessel, more resistance. So what about instead of the fluid flowing and being viscous, what if we drop an object in a fluid that is viscous? And this is where we get something called viscous drag. So when an object moves through a fluid, the fluid exerts a drag force or a resistive force on it. So it kind of slows this object down. So when the relative velocity between the object and the fluid is low enough for the flow around the object to be laminar, the drag force drives from viscosity and is called viscous drag. So viscous drag is proportional to the speed of the object, meaning the faster that this object moves, the more viscous drag there is. It also has to do with the size and shape of the object, can make a huge difference. This has to do with surface area. So motion of objects through viscous medium, right? When an object goes through a medium, even air, it experiences a resistive force. So I told you whenever we were in mechanics that we were going to neglect air resistance. What we're now talking about is this sort of resistance that was neglected, this drag force. But we are only going to apply it to fluids. So imagine trying to walk through air versus trying to walk through water versus trying to walk through a pool of honey. The more viscous the medium, the more it slows you down. And viscous fluids resist motion, right? These molecules stick together and they resist any sort of deformation. So the instant any sort of object begins to fall through this viscous fluid, the force of friction is zero because the speed of the object is zero. But as this object begins to accelerate and speed up, this force of resistance, this drag force, also starts to speed up until you hit something called terminal speed or terminal velocity. And this is when the net force goes to zero. So this occurs when the net upward force of the drag force balances out the downward force of gravity, right? So this terminal speed or terminal velocity is the fastest that an object can move through a medium. And we can calculate this using Stokes' law. So Stokes' law tells us what this resistive force is. And it's important to note that this specific equation for Stokes' law is only applicable for a spherical object. 6 pi, this has to do with the shape of the object. Eta is our viscosity, r is our radius, v is our velocity. Small objects fall slowly, more surface area, and more drag relative to the mass. The higher viscosity, the more resistance there is. Example, red blood cells moving through plasma, right? Blood is our viscous medium. The effect of this is that movement is slow and diffusion is key to the actual motion. We can also see this thinking of like mucus clearing in your lungs, right? So mucus is highly viscous. So the cilia must overcome the viscous drag to, I don't like the word pumping, because they kind of like flap, right? To flap the mucus out of your lungs. We can see the same thing with a microorganism swimming, as well as drug delivery in tissues. So how do we calculate this? Well, let's say that I have some sort of viscous medium here. Let's assume it's honey. And I drop a rubber ball in this, right? So I want to think about the forces here. Well, I have that resistive force pointing up, right? That's my drag force. I have the weight of the object pushing down, but I also have that buoyant force wanting to buoy this thing up. So I have 2 forces up, 1 force down. I already rearranged it. So I have my definition from Stokes' law for the drag force. I have buoyancy, which is the density of the fluid times gravity times the volume of the fluid that has been displaced. And because this ball is fully submerged in my fluid, the volume is going to be 4/3 pi r cubed, right? The volume of my sphere. And then I also have the weight of my object, right? And this is going to be the density of the object times g times the volume of the object, which is again 4/3 pi r cubed. So I can plug this all into my equation. And if I solve for this velocity, this is my terminal velocity. And I get an equation for the terminal velocity. And this is the max speed that this object is going to be able to move through this medium. And it's determined, remember that this is only for a spherical object, by the radius of the object. So the smaller the radius, the faster it moves. The viscosity of the fluid, and the difference in the densities, the difference in the density between the density of the object and the density of the fluid. Now, what if we have an object that is not a sphere? Well, we still have the same initial equation. Let's assume, like, I don't know, it's oddly shaped. Not like a cube, not something that we know the geometry for, a blob. Well, we can represent the resistive force with K times Vt, right? Vt, terminal velocity. And K is going to be something called our coefficient of proportionality. Generally, this is determined experimentally. And I'm going to represent the buoyant force and the weight. The weight I'm just going to have as mg in this situation. And my buoyant force is going to be the difference between the densities here times mg. And here are the equations that I use for this. So in this case, we have a new equation for the terminal velocity of this object. The problem here, I need to know K, and K is determined experimentally. So for a sphere and for a non-spherical object, the equations are fairly similar, but there are slight differences. An example of motion through a viscous medium is going to be things like biological fluids, right? So the terminal speeds of biological fluids are generally very small because there is such a high viscosity and such a small size of the particles, right? So for blood cells falling through plasma, it's about 5 centimeters per hour. So pretend you're a phlebotomist, you go draw my blood. Generally, they don't just wait for the blood to settle, right? They put it inside of a centrifuge. And this is because plasma falls at 5 centimeters per hour in the gravitational field of the Earth. So this is really, really, really slow, especially when you need like diagnostic testing, right? So this is the sedimentation rate, right? It refers to how quickly particles fall through a fluid. And this can be important in diagnostics, but we can actually increase the sedimentation rate in a fluid by making it feel a g-force greater than 9.81. And this is done in a centrifuge by adding on this very high centripetal acceleration, right? So under the conditions, whenever you put like a test tube inside of a centrifuge and you spin it really, 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 really fast, the objects actually gain a large radial acceleration that is much greater than free fall acceleration. So we replace our g in the equation with the angular acceleration. And we can increase the terminal velocity of the object, right? We can increase the sedimentation rate so that we're not waiting for 5 centimeters per hour. And the last thing I want to talk about a little bit is surface tension. So surface tension can be thought of as the energy of a fluid at its surface, right? So in equilibrium, an object's energy is a minimum, right? If we think about the potential energy of a ball whenever it's sitting on the ground, it is at a minimum. So in equilibrium, an object's energy is at a minimum, right? So to minimize their energy, fluids actually take on a shape so that its surface area is as small as possible. And that's why water droplets form this spherical shape, is because it actually has the smallest surface area. So it has minimized its energy. The surface tension, this is gamma, it's like a little fishy upside down, can be determined and is equal to force divided by L, where L is the length of the object's contact with the surface of the fluid. So if we have a sphere, right, we want the diameter of this surface. And there are interesting things with surface tension. So just like viscosity can change with temperature, surface tension can also change with temperature. And that's because whenever you increase the temperature, you are increasing the speed of the molecules. And so these molecules are not bound as tightly together. But there's another way that we can decrease the surface tension of an object, and that's with surfactants, right? So actually what happens whenever you put your soap in the washing machine, like what it's actually doing to your laundry is the soap, right, the surfactant is decreasing the surface tension of the water so that the water can flow in between the like crevices of your clothing to clean them better. That's the purpose of laundry detergent. It is just to break up the surface tension. Well, I mean, there's other things, right? Like it has like good smells. But the main purpose of soap is to break up surface tension. And that's why when you wash your clothes with soap, it does better than just plain water, is because now the water can go into like the cracks and crevices and in between the little fibers in your clothing.